Cardiovascular system, cardiac physiology. Afterload can be thought of as the load that the heart must eject blood against. In simple terms, the afterload of the left ventricle is closely related to the aortic pressure. To appreciate the afterload on individual muscle fibers, afterload is often expressed as ventricular wall stress. Wall stress is proportional to ventricular pressure times ventricular radius over wall thickness. This relationship is similar to the law of Laplace, which states that wall tension is proportionate to the pressure times radius for thin-walled spheres or cylinders. Therefore, wall stress is wall tension divided by wall thickness. The exact equation depends on the cardiac chamber shape, which changes during the cardiac cycle. Wall tension follows Laplace law. Wall tension pressure, wall tension equals pressure times radius. Wall stress is proportional to pressure times radius over 2 times wall thickness. At a given intraventricular pressure, wall stress and therefore afterload are increased by an increase in ventricular inside radius, ventricular dilation. A hypertrophied ventricle, which has a thin, thickened wall, has less wall stress and reduced afterload. Hypertrophy, therefore, can be thought of as a mechanism that permits more parallel muscle fibers to share in the wall tension that is determined at a given pressure and radius. The thicker the wall, the less tension experienced by each sarcomere unit. Stroke volume equals N diastolic volume minus N systolic volume. Ejection fraction equals stroke volume over N diastolic volume. In other words, N diastolic volume minus N systolic volume over N diastolic volume. Ejection fraction is an index of ventricular contractility. Ejection fraction decreases in systolic heart failure. Ejection fraction is usually normal in diastolic heart failure. Cardiac output equals stroke volume times heart rate. The Fick principle states that blood flow to an organ can be calculated using a marker substance if the following information is known: amount of marker substance taken up by the organ per unit time, concentration of marker substance in arterial blood supplying the organ, concentration of marker substance in venous blood leaving the organ. Fick principle, cardiac output equals rate of O2 consumption over arterial O2 content minus venous O2 content. Fick equation, cardiac output equals oxygen consumption in milliliter of pure gaseous oxygen per minute over oxygen content of arterial blood minus oxygen content of mixed venous blood. In early stages of exercise, cardiac output maintained by increased heart rate and stroke volume. In later stages, cardiac output maintained by increased heart rate only. Stroke volume plateaus. Pulse pressure equals systolic blood pressure minus diastolic blood pressure. Mean arterial pressure equals cardiac output times total peripheral resistance. Mean arterial pressure at resting heart rate equals 2/3 diastolic blood pressure plus 1/3 systolic blood pressure. In other words, diastolic blood pressure plus 1/3 pulse pressure. Isovolumic contraction period between mitral valve closing and aortic valve opening, period of highest O2 consumption by the heart. Increased contractility, increased stroke volume, increased ejection fraction, decreased end systolic volume, increased afterload, increased aortic pressure, decreased stroke volume, increased end systolic volume.